Hey there! How's it going, everybody? In this video, we're going to overcome the challenges in setting up an IPSec VPN through a NAT. We'll be using Juniper SRXs as our VPN peers, IKEv2 for the Phase 1 tunnel with pre-shared keys for authentication, and our Phase 2 tunnel will be route-based. We're also going to look at NAT Keepalives and NAT Traversal and what they do for us. We're not going to review fundamentals such as IKE authentication or how IKE and IPSec interoperate, so if you'd like to review that, please check out the previous videos on my channel. Alright, let's begin. Before we talk about how network address translation affects IPSec, let's review the three types of NAT. First, we have static NAT. This is a one-to-one model of NAT, where we have a local host and one global IP, and we set up a translation rule to translate that one local host to that one global IP. And so this NAT is called symmetric because the number of local hosts has to equal the number of global IPs you have available. That said, if you have a large range of local hosts and global IPs, you can use a range command for ease of use. So 0.0/24 translating to 102.0/24. Now this is still symmetric and one-to-one static NAT. It's just a command that covers 256 translations for ease of use. So 0.100 would translate to 102.100, 0.200 would translate to 102.200. Notice how static NAT by default doesn't translate the port, and it doesn't need to because the global IP is dedicated to the local host, and so the local host has access to all the ports of the global IP, and so port translation doesn't happen by default. That being said, there is a concept of static port translation, where let's say you want to listen on port 22 on your local host, but you don't want to listen on that port on the global network, so you set up a translation for port 8022, so that when a host on the global network connects to port 8022, it gets port translated to port 22 for your local host. The next thing you need to know about static NAT is that it persists through disruption. So if the NAT device goes down, or the local host goes down, or the local host is inactive for a long period of time, all the static NAT rules are still in place. So once services resume, NATing resumes to the IP as expected without any problems. Finally, because the global IP is static and not changing, it's practical for a host on the global network to know what that IP is and therefore can initiate traffic to that IP and get denatted and connected to the local host. So you have a two-way initiation capability with static NAT. The next type of NAT is dynamic NAT, which is a many to few model. Here we have a local range of hosts, but a smaller range of global IPs. And so we set up a rule to translate our local hosts to this global range on a first-come, first-served basis. And you'll notice that since these inside hosts are being given the entire IP from the global range, there's no port translation by default. Because again, each of these local hosts have access to the entire global IP they're being granted. Now, because there's a limited amount of global IPs, there has to be some mechanism for the NAT device to determine when to maintain the binding or when to surrender a global IP back into the pool for another local host to use. And so dynamic NAT devices will monitor the activity of the inside hosts and also have a timer. And if a local host is inactive, meaning not sending or receiving traffic for a long enough time, then the translation will time out and a global IP that was being used will be surrendered back into the pool for another local host to use. And this can create problems for certain types of applications that are quiet for long periods of time, where maybe there's a connection going on to a host in the global network, but whatever the application is, it's quiet for a long period of time. The inactivity timer can be reached. This binding can be flushed out and this IP can be surrendered back into the global pool. And the inside host and the global host doesn't know that. Then when traffic resumes in either direction, if it resumes from the global side, the traffic is dropped. If it resumes from the inside, then either the inside host doesn't get an IP because there's no IPs left and the traffic is dropped, or it could be given a different IP, and then this traffic proceeds to the global host on a different IP and confuses the global host. So dynamic NAT can create problems for certain types of traffic where there's long pauses. Another problem with dynamic NAT is that it doesn't persist through disruptions. So if the NAT device goes down, or if a local host goes down, then that translation, that mapping, will be cleared out. Also, like we spoke about before, if the local host is inactive for a long period of time, or if an administrator logs in and clears out the translation, those two could also clear out the mapping and cause problems. Finally, with dynamic NAT, there is a way for a host on the global network to initiate traffic to the global IP and be connected to the local host. But this isn't always practical because it's difficult for the global host to reliably know which global IP was dynamically given to the local host it wants to talk to. And so dynamic NAT isn't normally used in this way, but it can be. The final type of NAT is NAT Overload, which is a many-to-one model. This is where we again have a local range, but we only have one global IP. And so we set up a rule to translate our local host to the same global IP and use port translation. And that's why this is sometimes called port address translation. And you can see here as these hosts initiate traffic through the NAT, each one of their connections is NATed to the same global IP but on a separate port. So NAT Overload shares the same problem with dynamic NAT, where the timer is watching the activity of the local host, and if that timer is reached, then the port translations can be cleared out and surrendered back into the available pool of ports. Additionally, if the NAT device goes down, or if the local host goes down, or if the local host is inactive for a long period of time, or if an administrator logs in and clears the translation, in all four cases, the translation can be lost and cause connectivity problems for ongoing but quiet applications out to the global network. Just like in the dynamic example, if the timer is reached and the binding is lost, then what can happen is the local host can be given another port, which can confuse the global host who's not expecting traffic from that IP on that port. Finally, NAT overload is not two-way initiate like static and dynamic, because the only ports that are open and being listened to are the ones that already have translations from ongoing connections. So if a global host tries to initiate on another port, the NAT device isn't listening on that port, and there's no translation back to anything on the inside, and so that traffic is dropped. Before we move on, I'll point out that all my examples here are source NAT, and I don't have any destination NAT examples. And that's because source and destination NAT are simply a matter of perspective. Consider that if you're a host on the global network initiating connectivity to this global IP, your destination IP is being NATed to the private IP of the local host you're trying to connect to. So source and destination NAT is really a matter of perspective, and they affect IPSec in the same way. And so just for simplicity, all my examples will use source NAT. And the same goes for twice NAT, where you're translating both the source and destination IP at the same time. Twice NAT affects IPSec in the same way source NAT does. Now, when we're going to do an IPSec VPN through NAT, there's two features that we want to be aware of. The first is NAT Keepalive. NAT Keepalive is where the IKE process sends an unencrypted packet. This is after the IKE tunnel is up, after the IKE exchange is up, after IPSec is up. IKE sends an unencrypted heartbeat packet of only 1 byte to the peer, and it doesn't expect the peer to respond. The peer just discards it. And the purpose of this packet is to refresh the dynamic NAT or the NAT overload translation timeout. Since both dynamic and overload NAT have translation timeouts for either the IP or the port respectively, this feature keeps that translation alive. That way, if it's a quiet VPN without a lot going on, then you don't have the problem where the translation times out, and then all of a sudden IKE wants to say something, and IKE gets mapped to a different port, and now the peer thinks something's wrong and clears out the entire IPSec session. The next feature you need to know about is NAT Traversal, or NAT-T, also known as UDP encapsulation. What this does is if NAT is detected during the IKE exchange, then IKE switches over to use UDP 4500 instead of UDP 500. And IPSec is encapsulated in UDP 4500. So if you remember, normally IPSec is protocol 50, its own layer 4 protocol. Well, that presents a problem for NAT, because when you do a NAT overload specifically, it's making translation decisions based on the IP address and source port, but ESP has no concept of port. It has a sequence number, it has something called SPIs, but there's nothing in the layer 4 ESP header that is represented by a port. And so the NAT device has no way to correctly make the NAT mapping, not a traditional NAT device anyhow. So let's take a look at this. So here's the IKEv2 pre-shared key exchange. And you'll notice that we have SRX0 and SRX1. SRX0 has started the exchange by sending the first init packet. So it's the initiator. And in the first init packet, like we've covered in previous videos, are the IKE proposals, which are the settings we want to use for the IKE tunnel, the Diffie-Hellman public piece, the one-time use random number, or the nonce. And then see this right here? This is the NAT discovery block. Whenever you have NAT traversal turned on, and I should mention it's on by default, then this NAT discovery block is put in the init packet. And the NAT discovery block is a hash of 4 things that both peers already know: the source port, the source IP, the destination port, and the destination IP of the IKE session that it wants to establish. When the init packet gets to the other side, to SRX1, SRX1 looks at that NAT discovery hash, and it runs a hash of the same 4 things. And if the hashes don't match, it knows that one of those 4 things was translated by NAT, and it knows there's a NAT. And because this init happens in both directions, because SRX1 responds to SRX0, and it responds with its own NAT discovery block, so SRX0 is able to discover the NAT as well. When both peers discover the NAT, they both switch over to UDP 4500 for IKE. And when the auth packets are exchanged, these are exchanged on UDP 4500. And if the authentication process is successful, then the ESP gets encapsulated in UDP. A UDP header goes in front of the ESP traffic. And what this does is it is for the purpose of helping the NAT device. Since ESP doesn't have any ports in the layer 4 header, and a NAT overload device is looking for a port in order to translate, it puts the UDP header in front of the ESP header and behind the IP header. That way the NAT device says, hey, there's the port I'm looking for. Now I can make this translation. Now a bonus side benefit of having both protocols use UDP 4500 is that now you only have one NAT binding to worry about. You might have been like, hey, why don't they just use separate ports? Why can't IKE stay UDP 500 and why can't ESP use UDP 4500? Well, one nice benefit of having them use the same port is now there's only one NAT translation or binding you have to worry about, only one NAT timeout you have to worry about. Now, and this is why if you use NAT Traversal, you normally don't need to use NAT Keepalives. Because with NAT Traversal, you normally in modern VPNs have enough traffic to reset the timer on the UDP NAT translation of a normal NAT device. If you don't, then you're still going to need NAT Keepalive. But if you do, then you don't need it, because now either your IPSec traffic or your IKE traffic, whichever one in either direction, is going to refresh the NAT binding. So let's talk about what's going on here, because actually a lot of people think, and you'd be forgiven for thinking this, that NAT Traversal exists for the purpose of that NAT breaks the integrity check on either IKE or IPSec. And that's actually not the case. So I wanted to show you the different types of IPSec. In our series on this channel, we've only done the bottom type, the ESP tunnel, but there's 4 types. You have authenticated header, and you can do that as transport or tunnel, and you have encapsulated security payload, and you can do that as transport or tunnel. So I just want to go through these so you see how they work and how they're affected by NAT. So if we're talking about authenticated header, transport, you'll notice something. It adds one header, so the white is the original packet and the red is what's added. So authenticated header adds one header of 24 bytes. So if you had a 1400 byte packet, it now just increased to 1424. But the integrity check spans the entire packet. And guess what NAT does? NAT is translating stuff in this IP header. Now, to be fair, to be specific and precise, authenticated header, there's certain things in this IP header that authenticated header does not integrity protect, namely the time to live, as well as some other things like quality of service. But it does protect the source and destination IP, source and destination port. So NAT utterly breaks authenticated header. Authenticated header is not compatible with NAT. And NAT Traversal does not fix that. So if you have a NAT, you can't do authenticated header. But also notice, just as a quick aside, authenticated header doesn't give you any encryption. So no confidentiality, no privacy, whatever you want to call it. It just gives you integrity check. And so it's called authenticated header because you're authenticating the packet itself, the authenticity of the packet, that it hasn't been changed in transit from the sender. If you look at authenticated header in tunnel mode, it works the same except it adds a new IP header. So now what this does is it hides, not through encryption, but it hides the original packet header from the untrusted network in the middle, presumably because you're using private IPs. That's the reason why you do this. But the integrity check still covers the new IP header. So even authenticated header tunnel mode is incompatible with NAT. And you can see here, because of the extra header, it's 44 additional bytes that gets added. So then we come here to encapsulated security payload, transport mode. This, you keep your original IP header and you encrypt the layer 4 and up of the original packet, and then you put an ESP header on. This is the IP protocol 50. This is the part that doesn't have ports on it, which makes it incompatible with NAT overload. And then you have an ESP trailer and an ESP authenticating or authentication trailer. So a couple things. First, you'll notice that the integrity check doesn't cover the IP header, even in the case of transport where it's the original IP header. So ESP is compatible with NAT, because if you're doing NAT static NAT or if you're doing dynamic NAT, no problem. It changes some IPs in this header. That's not the integrity check for ESP, doesn't cover that, so that's no problem. Another thing I want to point out is notice how this ESP trailer is covered by the encryption. What's going on there? We want our traffic to be encrypted. So why is this thing being added? Well, with ESP and encryption, you're using block ciphers. And block ciphers require the data you're encrypting to be multiples of a certain number. And the common block ciphers for IPSec are AES, namely AES 128, 192, 256. And that requires your original data to be multiples of 16. So one of the purposes of this ESP trailer is to add padding to your layer 4 and up data to make it a multiple of 16 so that it can be encrypted by the AES block cipher. That's what all but 2 of the bytes are in this packet. There's 2 bytes in this packet that have other purposes. So in this example, all these numbers are correct. I did the calculations. In this example, there's 6 bytes of padding to make this work. And that's why I have this tilde here, because with ESP, you are dealing with variable length post-encryption packets, based on the length of your pre-encrypted packets because of this multiple of 16 requirement and the variable padding length. The padding can be anywhere between 0 and 15. 0 if your original data is already a multiple of 16, or 15 if it's only one off, and then of course everything in between. And so now if we talk about this authentication piece, when an ESP packet is received, the first thing the peer does is look at the authenticating trailer, do the integrity check, make sure that this packet wasn't manipulated in transit. If it was, discard it. Don't bother trying to decrypt it. But if it passes the authenticity check, the integrity check, and the packet is authenticated, then it begins the decryption process. And in this ESP header, even though it doesn't have ports, it does have sequence numbers, which is important if you need to reorder these packets, right? If they got out of order in transit. And it also has something called the SPI values, which are the special identifiers that are negotiated in the IKE tunnel that no one else knows about, that tell the peer which IPSec SA this belongs to, so it can use the correct key to decrypt this packet. So I just kind of want to point that out. And you can see here we're talking about 44 bytes of overhead in this case with these numbers for ESP transport. So then we go to the mode that's by far the most popular, and that's ESP tunnel. And again, this one, just like authenticated header tunnel, adds a brand new IP header onto your packet. And this allows us to use private corporate IPs that aren't routable on the untrusted network. It hides our destination source IPs, even if they were routable, which is nice. And again, because this IP header is not covered by the integrity check, no problems with static NAT or dynamic NAT. None at all. And everything else that applies to transport mode that I spoke about just now applies to tunnel mode, as far as the sequence numbers and the SPI values and the ESP header, the padding that's variable length in the ESP trailer, and the authenticating trailer that's checked first to check the integrity of the packet before it even attempts to decrypt it. And you can see with this example of a 1400 byte packet, it's 60 bytes of overhead. So there is a decent amount of overhead here, which is why it's common to scale back your MTU of your tunnel interface, because normally you're using the internet or a 1500 byte transport in between your peers, and you don't want there to be fragmentation. And let's talk about that since we're here. Why do you think fragmentation would be a bad idea? What do all of these have in common? Integrity checks. And guess what breaks integrity checks? Fragmentation. Any of you out there who have ever tried to SSH through a segment of your network where there's fragmentation know what I'm talking about. Because fragmentation even breaks protocols like TCP/22 SSH, which is encrypting at layer 4 and up. Same idea here, right? This is encrypting layer 3, and it expects the packet to not have been manipulated in transit. And fragmentation breaks your packet into 2 packets and definitely manipulates it in transit. And even if it's reassembled by another device, it doesn't matter. The integrity check is now failed, and this will be discarded. So again, keep in mind of these overhead numbers when you're doing IPSec, and adjust your configurations accordingly. So now that we're aware of what these packet formats look like, let's talk about how NAT-T comes in and saves the day. So sorry to say that NAT-T is not supported for authenticated header. Doesn't do anything. So if you're doing authenticated header, you can't have a NAT in between. It breaks the integrity check, and NAT-T can't save you. Let's look at what it does for transport mode and then tunnel mode though for ESP, because it does save the day for us when it comes to NAT overload. So what it does is it encapsulates your IPSec traffic, your ESP traffic, in UDP. And see here how it inserts a UDP 4500 header in front of your already existing ESP header. And notice the UDP header is 8 bytes there. So this is 8 more bytes of overhead. Now what does this do again? This gives the NAT device a port to look at. A NAT overload device wants the source IP and the source port to make the translation to the one global IP. And it doesn't have that with ESP because ESP has no ports in the header, only sequence or SPI numbers. With this NAT traversal, you encapsulate your ESP with UDP and you give it a port to play with. You give the NAT device a port to reference so it can make the translation. Also, look down here with tunnel mode. Same situation. You still have the new IP header in which the NAT action is going to happen on, and you have the UDP packet that's put after the IP packet but before the ESP header. And you can see here, this is the ultimate overhead right here. 68 bytes of overhead when you have NAT-T enabled. So that's why a lot of people, like me included, will just plan on only sending 1400 bytes into an IPSec VPN, just so the math is easy and you don't have to keep track of changing numbers based on the padding. So right here you might be asking, wait a minute, we got a problem. You're telling me that IPSec is going to go through the NAT device with UDP 4500, and you said earlier that IKE is going to go through with UDP 4500. That's going to make the NAT device think that's the same session, the same flow. And you'd be right. That's exactly what we're doing. We're fooling the NAT device to think that our IKE and IPSec is the same flow, so that there's only one translation both peers have to worry about. And that's going to make it so that it's less likely that that translation times out, because either IKE or IPSec traffic will refresh that translation. And if for some reason you have a quiet IPSec tunnel, then you could turn on NAT Keepalive to prevent it from timing out. But you might be thinking something else, like, wait a minute, well-behaved IP devices use port numbers to determine what process to hand traffic off to. So if this gets to the other peer and it's IP UDP 4500, how does the peer know that what's after the UDP header is either IKE or ESP? And that's a great question. Here's how. When we transition to NAT-T, ESP works just as I told you, and the peers expect ESP to be after the UDP header. So IKE has to do something special. This is what a normal IKE packet looks like, and IKE uses really small segments. It's not saying a lot in the upper layers, so I'd even put the value, but it's small. It's in the hundreds. But here's your 20-byte IP header and your 8-byte UDP 500 header without NAT-T. When IKE does NAT-T, look what it does. It doesn't just switch to UDP 4500, 8 bytes. It adds a non-ESP 4-byte header right after that, because the peer is going to expect that after the UDP 4500 is ESP, and it's going to want to send it to the IPSec process. And that makes sense because your IPSec is your noisy data channel where 99% of your data on port 4500 is going to be going to. However, if IKE has to say something and it talks over UDP 4500, it puts this non-ESP header right after the UDP 4500 header, and that tells the IPSec process, whoa, send this to IKE. This isn't for you. So it has that pretty cool feature. So now both IKE and IPSec can share the same UDP port, but won't confuse the peer. Now, while NAT Traversal is a wonderful and useful feature, it only helps us with NAT Overload, the type of NAT that needs a source port for translation. There's actually problems caused by all NAT, including static NAT and dynamic NAT, that NAT-T doesn't help with. And those problems begin in the third and fourth packet of the IKE exchange, the auth packets. If you see here, one of the things that is exchanged between the two peers is their IKE ID. Now what's interesting is both peers already have an opinion on what their IKE ID is and what their peers should be. And when this IKE ID is exchanged between the two, this is a validation step. This isn't a learning step. And so if this IKE ID doesn't match, then the IKE authentication will fail. So this leads us into our first problem. And this problem is caused by all NAT types. And so this problem has to be overcome no matter which NAT you're dealing with. So if you look at this topology here, we have a static NAT. And we're NATing SRX1's local IP into this global IP. Now over here on the left with SRX 0, you can see it has the peer address configured as the public address. And this makes perfect sense because that's the address that's reachable. He can't reach this private IP over here. It's not routable through the untrusted internet. The second thing you'll see is that he has his external interface configured. These two spots in the config is where SRX 0 derives what the local and remote IKE ID should be. He thinks his local IKE ID should be the IP address on his external interface, and he thinks the remote IKE ID should be the peer IP. And so that's why up here we have SRX 0 saying my IKE ID is the 138.98 IP and yours should be the 102.61 IP. But look over here with SRX 1. SRX 1 has its external interface set to gig 000, and so it thinks its IKE ID should be this local IP address. So he says my IKE ID is 0.101, this private local address. Now the good news is he is correct on what the remote IKE ID should be because SRX 0 isn't being natted. So they both agree what SRX 0's IKE ID should be, but they disagree on what SRX 1's IKE ID should be. And when SRX 1 sends its auth packet to SRX 0, it's going to say my IKE ID is 0.101. SRX 0 will not accept this, and authentication will fail, and the IKE tunnel will go down. And again, this affects all NAT types. So if you're doing IPSec through a NAT, then you have to overcome this. So the problem restated is all NAT types cause the default IKE IDs, which are interface IPs, to mismatch. And the solution is that the IKE ID of the natted peer needs to be configured. And there's a few ways to do this. Way number one is over here on SRX 0. We can configure the remote IKE ID to be the private IP, the actual IP of SRX 1. Now, the remote IKE ID of SRX 0 will match the local IKE ID of SRX 1 and authentication will pass. The second way to do this is over on SRX 1, where we can make the local IKE ID the public IP that we're being natted to, which is the same IP that SRX 0 has as the peer address. This again makes SRX 1's local ID match what SRX 0 has the remote ID. And the third way to do this is to just switch the IKE ID to something else, like let's say a host name. So we could configure the remote IKE ID on SRX 0 to be SRX 1 and the local IKE ID on SRX 1 to be SRX 1. Now they both agree on what the IKE ID for SRX 1 should be. Let's take a look at the topology we'll be using. And this topology is going to be using static NAT. I chose that because the IKE ID problem is the only problem presented by static NAT. You don't need NAT Traversal and you don't need NAT Keepalive. So if you can solve the IKE ID problem, then you can do IPSec through a static NAT. So over here on the left, we have SRX 0, and you can see it's got a loopback IP of 10.0.0.0. Over here we have SRX 1 with a loopback of .1, and over here we have SRX 2 with a loopback of .2. And SRX 1 and 2 are going to be traversing the same NAT. However, they're both going to be getting their own global IP address. All right, and then we're going to have two tunnels, one for each SRX, tunnel 1 and tunnel 2, going to SRX 1 and 2 respectively. And the IP addressing is kind of obvious. The third octet is going to be .1 and .2 for SRX 1 and 2 respectively. All right, so here we are on SRX 0. And before we get started, let me mention that SRX 0, 1, and 2 are already configured. What we're going to do is look at the devices and their configuration, see what's going wrong because of the NAT, and fix it. If you're interested in learning how to configure an IPSec VPN between SRXs, either using pre-shared key or certificate authentication, then check out the previous videos on my channel. I cover that. So because we're verifying, we're actually going to be moving pretty quickly here. So let's get started by making sure that we're in flow mode, because SRXs have to be in flow mode to do IPSec VPN, and we are. Next, we'll look at our interfaces, and it's what we expect. We have our internet interface, which is 000. We have our loopback interface, and we have our two tunnel interfaces, one going to each SRX 1 and 2. Let's take a look at our routes. All right, so here's our 10.0.0.0 loopback IP. Here's our internet facing interface and IP 138.98. And here's our static default route, which is next hopping to our ISP 138.97, going out our internet interface. And then here you can see we also have our secure tunnel direct routes 1.0 and 2.0. And this OSPF route here doesn't mean we're neighbored, it just means that OSPF is running on the interface. So we can verify that real quick. We have no OSPF neighbors right now. So let's continue looking at the configuration by looking at our security zones, because with SRXs in flow mode, you have to have every interface in a security zone for it to function. So we have our internet zone with our internet interface, and we're allowing pings and IKE to come in. Now, this IKE will also allow IPSec, which is what we want. Then we have our corporate zone, which is allowing all services and protocols, and so OSPF will be allowed. And we also have our loopback interface and both of our tunnel interfaces. So that's perfect. That's corporate is going to be our trusted zone. So now let's look at our policies. This is what's going to allow inter and intra zone traffic. And in our case, we just need intra-zone traffic. So we have a from corporate to corporate intra-zone policy, and it's going to permit any source, any destination, any application, which means any protocol, then permit. So all that is exactly like we expect. So let's go ahead and try to ping the global IP of SRX1 and see what happens. All right, it works. And let's, while we're here, ping the global IP of SRX2. And it works as well. So it's reasonable to assume at this point that SRX1 and 2 are up, and the NAT is configured and up. And so let's continue looking at the IKE and IPSec configurations on SRX0. So for IKE, we have our proposals. You can see we're using pre-shared key, group 14. Here's our policy, which has our pre-shared key configured. Here's a really cool command: request system decrypt password, and any $9 password you can actually decrypt. And so the password we're using is this is a NAT lab. All right, so now look at the gateways. We have a gateway for SRX1 and a gateway for SRX2. They're both referencing the same policy, that's fine. They're both pointed to the separate global IPs. You can see NAT traversals turned off for both of them. That's on purpose. We don't want NAT to be detected. We don't want to jump over to UDP 4500 and encapsulate IPsec in UDP, because I'm demonstrating how this first problem, this IKE ID problem, is not solved by NAT-T, and you don't even need NAT-T for static NAT. We're running version 2, and of course our external interface. So let's take a look at IPsec, see what that looks like. So our IPsec, we have our proposal encapsulated security payload, so that is compatible with NAT. Perfect forwarding secrecy on our policy here, and then we have our two VPNs, one for each peer, both referencing their separate gateways, but both sharing the same IPsec policy, which is fine, which means we'll just share the same proposals and perfect forwarding secrecy settings, and they're both bound to separate tunnel interfaces, which is perfect. So let's look at those tunnel interfaces. And this is what we'd expect. .1 is going to SRX1 using IP 1.0, and 2 is going to SRX2 using 2.0. So everything is looking really good here. And finally, we'll look at our OSPF, and it's configured as passive on loopback 0 and regular on our tunnel interfaces. So we've already looked earlier, but you saw OSPF isn't up. And let's just check and see. I should be able to ping myself, but I shouldn't be able to ping the other side if it's down, which it looks like it's down. And I can't ping the other side of the one going to SRX2 either. So let's look at some commands here for IKE, see what's happening. So we don't even see anything here. It says no IKE security associations at all. Let's look at IPSec, and we'd expect to see nothing here because IPSec is a child of IKE in the IKEv2 model, so no IKE means no IPSec. So let's look at our inactive tunnels. This is a super useful command because it shows us what tunnels are configured to be up but are not up and why. So here you see the first evidence of what we were talking about before. It's saying the peer's IKE ID validation failed during negotiation. So this is the same problem we talked about before, where we're configured with this 102.61 global IP, and we don't have the remote IKE ID manually configured. So it's inheriting this IP address as the remote IKE ID. But SRX1 and SRX2 aren't using these global IPs as their IKE ID. and so that validation is failing. There's a couple other things though that I kind of want to show you. One of them is show security IPSec statistics. Now this is really useful because sometimes when you're troubleshooting IPSec, you'll have like an oscillating tunnel where it's up for a little bit, then it's down. These statistics accrue until you clear them. So the fact that we have never successfully sent an encrypted packet or received a decrypted packet, that's useful information to know, right? So now we're talking about, hey, this has never been up, it's never been functioning. Now let's look at our tunnel event statistics. This is kind of like an aggregation of all your IPsec tunnel events, and it shows you how many times things have happened. So this is really good when things are cycling and something's not working, and so you keep getting a recurring error. So you can see here that 138 times we've gotten this peer IKE ID validation failed. That's just because the IKE and IPSec VPN is continually trying to establish, and it's failing, but it doesn't give up, right, until we fix the problem. So this all looks exactly like we'd expect. Let's jump over to SRX1 and see what we see over there. All right, so here I'm on SRX1, and we'll go through the same exercise. There you are, we're in flow mode. All right, similar to SRX0, we have our internet-facing interface, we have a loopback, and we only have one tunnel because we're only talking back to SRX0. Let's look at our routes. And so here's where we start to see the differences, because we do have our loopback, which is the .1 IP, but our internet interface right here is actually a private IP, and this is what's connecting to the NAT. So our 0101 connecting to the NAT, and you can see our default route here, next hopping to the NAT device, out our NAT-facing, public-facing, internet-facing interface here. And you can see our secure tunnel interface, IP. All right, so let's check our security zone. All right, internet zone, internet-facing interface, allowing ping and IKE. Corporate zone, allowing everything for services and protocol, and our loopback and tunnel is participating. So just like very similar to SRX0, basically the same. So let's take a look at the policies. All right, so yeah, only one policy and only one is needed. It's going to be our intra-corporate zone policy. So from corporate to corporate, it's going to be permit any, so any source address, any destination, any protocol, then permit. That's perfect. So let's now, actually let's, we already did this, but let's go ahead and ping SRX0 just to be thorough. So this is the public IP of SRX0, what we're trying to connect to, and it works, so no surprise there. And now let's begin checking the IKE and IPSec configuration. So we're using the same proposals, so that's good. That's what we want. And remember, we would expect this, by the way, remember, because the error we're getting on SRX0 is that the IKE ID validation failed. Well, the IKE ID is sent in the auth packet. So if this doesn't match, you don't even send packet 3 and 4. You don't send the auth packet if the init packets aren't agreed upon, right? And the IKE proposals and the init packets. So of course these match. Of course, the pre-shared key doesn't get validated until the auth packets. We can check that. Request system decrypt password. Let me just check this real quick. Yep, and it's the same one. This is a NAT lab. All right, so then our gateway, go into the public or global IP of SRX0, disable NAT-T because we don't need it. External interface version 2. All right, so everything's looking good. Let's jump back to IPSec and look at those settings. All right, encapsulated security payload, perfect forwarding secrecy. All right, we're gonna have one VPN here, and it's gonna bind to the secure tunnel 0.1 interface. It's referencing the SRX0 gateway. So yes, everything's looking quite nice here. Let's check our tunnel interface. We should only have one of them. Go into SRX0. It's a .1 and it's going to be 1.1. So everything looks really good here. Let's do the final check of our protocols. And OSPF is running on the loopback and the secure tunnel. So when the VPN comes up, OSPF will come up. It should be down because from SRX0's perspective it's down, so it's got to be down over here. And this is all what we'd expect. So let's go ahead and see what's happening with IKE, right? We expect to see nothing. It's got to be down. Oh, look at that. Isn't that interesting? So on SRX0, it showed IKE is down. Here we are on SRX1, and it thinks it's up. So we have both of our cookies. So the init packets got successfully exchanged, obviously. And there's the remote address. Everything looks right. Let's look at the detail of this. So IKEv2, we're 0.101. Notice how we're using UDP 500, so NAT-T didn't trigger because it's not even turned on, so we're not cutting over to 4500 or anything. Here's all of our proposals. And you can even see the 2 packets in both directions, so both init packets and both auth packets. So if you look at this from this perspective, if you're only looking at this side, at this point you might think that IKE is not a problem, that IKE is up. And let's stop right here and talk about that for a second. If you recall from the slide when we talked about the 4 packets, SRX0 was the initiator, and that's the case right here. See how it's saying that I'm on SRX1 and I'm the responder? So what's happening is SRX0 is sending the first init, SRX1 is sending the second init, and both sides are happy with that. Then SRX sends the first auth packet, and SRX1 is accepting that auth packet because both sides agree that SRX0's IKE ID is this public global IP address. So when the third IKE packet from SRX0 gets SRX1, SRX1 accepts it, brings up IKE, and it probably brought up IPSec. But SRX0, so then SRX1 responds with the 4th packet, which is the second auth packet, and SRX0 doesn't like the IKE ID it sees because SRX0 and SRX1 disagree on what SRX1's IKE ID is. So it seems that we're in some asymmetry here where SRX0 is not authenticating SRX1, so it's keeping the IKE tunnel down, it's keeping the IPSec tunnel down. SRX1 is happy with the auth packet from SRX0, it's authenticating it, so it's bringing up IKE, and let's see, I expect to see IPSec up, which we do. So if we look at the details here, it's going to have all the settings we'd expect. It's the secure tunnel interface, DF-bit copy. Down here you can see the proposals that we agreed upon. So there's nothing here with the settings that jumps out, but the first sign that something wrong is in this tunnel events section, because you can see here that something is reoccurring. So we have IPSec SA negotiated successfully, IPSec SA negotiated successfully, and that's only almost 10 seconds later. And then again, almost 10 seconds later, it's renegotiated again. So you can see something is cycling here. Now look up here at the top, or there's right here and up at the top, initial contact received from peer, stale IKE IPSec SAs cleared. So what this is saying is because SRX0 is not successfully authorizing SRX1, SRX0 is clearing out IKE, not bringing up IPSec, and then it's just running a timer for probably about 10 seconds. And then SRX0, because the IPSec tunnel's down, but it wants it to be up, sends the initial init packet. SRX1 is in a weird position because it accepted the auth packet and it brought up IKE and IPSec from SRX0. But then 10 seconds later-ish, when it gets this init packet from SRX0, it goes, whoa, me and my peer don't agree on what's going on here because I just had initial contact init packet received from peer. So this must be a stale IKE or IPSec SA, and I'm going to clear it in hopes that the next time it won't go stale. So this is just normal behavior. This is just SRX1 is cycling through in hopes that that will fix the problem, but it won't. Another place we can see this is under the tunnel events, which is maybe a little bit more clear because it's not sandwiched between all that IPSec stuff. But you can see here the initial contact is just cycling through. We've at 121 times. Another thing that's really useful is we're running OSPF, right, on this tunnel interface. And since we're running OSPF, we should be sending out OSPF hellos. So if I say show security IPSec statistics, I expect outbound traffic. And I have that. So because we think the tunnel is up, and then every 10 seconds we just renegotiate and bring it back up, we're sending encrypted traffic to SRX0. SRX0 is not accepting it because its IKE and IPSec never come up. But notice how we're not receiving any packets from SRX0. So again, this is a really useful command to start to see what's going on. This is a one-way tunnel. SRX1 thinks it's up, SRX0 knows it's down, and we're just cycling every 10 seconds or so. All right, so let's fix this problem. So what I'm going to do is on SRX1, I'm going to set the local IKE ID. So if you recall, right now our IKE ID is just defaulting to our external interface. Let's change that. Let's set security IKE gateway for SRX0 We're going to set the local identity, and we get a pick here. For this one, we're going to do an IP address, so INET, and we're going to set it to the public IP that SRX0 has as our IKE ID. Since this is what SRX0 is using as the peer IP, it's what it's automatically setting as our IKE ID. So we're just going to match them, and we're going to commit that. All right. Let's give it a second and then see if OSPF comes up. There it is. So OSPF is up for 3 seconds, fully adjacent, so that's bidirectional. So let's just quickly run through our commands, like namely, let's look at these statistics. So there you go, boom. We're already decrypting traffic. So SRX0 must think it's up because now he's sending us encrypted packets. We're sending. Everything's looking really good here. Let's do a show route protocol OSPF. So then see we're learning the loopback. So now I should be able to do my ping test here. And I'm going to source it from my loopback to make sure that SRX0 is learning my loopback. So there you go. So now OSPF is up. The whole problem was solved by simply setting the IKE ID of the NATed peer, right? So I'm going to jump over to SRX2 because SRX2 has the same problem, right? On SRX0's perspective, both tunnels were down for the same reason. They're both going through NAT. So let's jump over to SRX2. Now I'm going to just save a bunch of time here. SRX2 is configured identically to SRX1, but it has a different IP address, external IP address. It's 0102 instead of 0101. And it has a different tunnel configuration slightly. It's unit 2 and it's using 2.1 instead of 1.1. So besides that, the security zones, the policies, the flow mode, the IKE, the pre-shared key, everything is the same. It's still got a single tunnel back to SRX0. And so we're going to see all the same stuff. We're going to see that it thinks IKE is up. We're going to see that it thinks IPSec is up. We're going to look at our statistics and see that the IPSec is one way. And so when we look at our tunnel events, we're going to see this oscillation of these initial contact packets. So everything's the same here. What I want to demonstrate, though, is not only that you can have multiple SRXs behind the same NAT with static NAT as long as they're using separate IPs, but I also wanted to show you that we can set the IKE ID to something other than the IP address. So maybe you want to make it obvious to fellow administrators, technicians, and engineers what's going on here. So maybe you don't want to just set the IKE ID to the global IP. Maybe someone won't know what that's doing. They'll clear it out, or they just won't know. So let's set it to something more obvious, like the host name. So we're going to say set security IKE gateway, and we're going to set the local identity to a host name. And we're just going to make it the name of this host, SRX2. All right, now let me jump back to SRX0. So over here, we're going to do the same thing. We're going to set the security IKE gateway SRX2, but this one's the remote identity. We're going to set it to a host name, SRX2. So let's see if that does what we want. All right, so it's starting to come up. Let's see if we're two-way here. Yes, we are. So it came up. We're two-way, full adjacent for 4 seconds. So let's look at the security associations. So I'm really interested in SRX2. We already know what's going on with SRX1. I'm really interested in SRX2. So let's do the index number here, and we'll do detail. So we're only looking at SRX2. So a couple things I want to point out. Number one, again, since NAT traversal is turned off, even though there's a NAT, it's not being discovered. We're not being cut over to UDP 4500. IPSec's not being encapsulated by UDP. And this demonstrates that you do not need that. You don't need it for static NAT. But look at this, the peer IKE ID SRX2, right? We still only have, the 2 init packets, the 2 auth packets. But now we both agree that SRX2's IKE ID is SRX2, and now there's no longer a mismatch. So if I look at my security associations, again, we'll use the index number, very useful. And we'll look at the detail. And yep, everything we'd expect here. SRX2 is the VPN name, IKEv2. And You can see the proposals that we agreed upon for phase 2. And yeah, everything's looking good. So let's just do something fun. I'm gonna jump back to SRX2 because now what I want to look at is we should be able to ping from SRX2 through SRX0 to SRX1, right? Because everything is now up, I should be learning the loopback of SRX1 through OSPF. So we'll do show route protocol OSPF. And there it is. So there's my loopback to SRX1. And you can see I didn't mess with the reference bandwidth for OSPF. So right now every hop is essentially 1 metric. So this is basically 2 hops away. So let's make sure I can ping this. So I'm pinging SRX1 via SRX0. And I'm going to source it from my loopback. So there you have it. So here you can clearly see that NAT Traversal has a use, but that use isn't to fix static NAT problems. The fix is the IKE ID. Alright, so this leads us to our second problem, which is caused by dynamic NAT. Now, dynamic NAT is gonna have the same IKE ID problem that static NAT has. All NATs have that problem. But dynamic NAT has a second problem, which is with dynamic NAT, the global IP address that we're natting our local host to is not deterministic, depending on network events, the NAT device restarting or going down or being administratively changed. All we know is the range. We don't know the precise global IP that our local host is going to be given. So here you can see SRX1, again, behind a NAT, again using a private IP 0.101, but now we have a range of global IPs, and we don't know which one on any given day, week, or month that is going to be given SRX1. And we don't want to be caught in a situation where we're making it work one day, and then something changes, and now it doesn't work the next day. So you can see what SRX0 is saying here. He doesn't know what to put for the peer address. SRX0 does not know SRX1's address, not reliably so. SRX1 has no problem, right? Because SRX0 isn't behind in that. So SRX1 has everything configured here that he needs. So the problem restated is dynamic NAT causes the natted peer to have a dynamic global IP. I mean, duh, that's the definition of dynamic NAT. But the solution is that the non-natted peer needs to configure dynamic mode using the IKE ID of the natted peer. So you can actually not have an address of a peer configured and instead configure something called dynamic mode. Now what's interesting is if you configure dynamic mode, there has to be something that anchors the peer to that gateway. So if you flush out the address, the peer address is what the IKE process uses to land a given peer on the right gateway. If you don't use the address and go in dynamic mode, then you have to use the IKE ID to land the peer on the right gateway. So this is kind of interesting how it works. Let's take a look. So here's the dynamic NAT topology that we're going to be using, and it's the same topology we used for the static NAT problem. So all the loopback IPs are going to be the same, the tunnel IPs are going to be the same, the tunnel numbers are the same, and even SRX0's global IP is the same. The only thing that's going to be changing is SRX1 and 2's global IP. Instead of natting them to those static single IP addresses, now they're going to be sharing this dynamic NAT pool, and so I changed the IP address to kind of highlight that difference. But all the other interface numbers, all the other IP addresses, and tunnel numbers are going to be the same. So let's jump in and see what we're going to have to do. We're going to have to make some changes since we're picking up right where we left off on SRX0 to get them out of the static peer mode and put them into a dynamic gateway, IKE gateway mode. Also, if you recall, we set the local IKE ID on SRX1 to the old public IP, the old global IP that we're no longer using, so we'll have to look at that as well. Alright, here we are on SRX0. We're right where we left off with the last lab, the static NAT lab, but now the dynamic NAT the natting has changed from static to dynamic, so now the global IP of SRX 1 and 2 have changed. So let's take a look at IKE and see what it's showing us. So yeah, this is kind of what you'd expect when you have both sides misconfigured, because our side is still configured to try to peer, statically peer with these old public IPs that are no longer in use. And then SRX 1 and 2 are now getting dynamically given these global IPs and are trying to talk back to us, and nobody's happy, everything's down. So we know what we need to do. Let's configure our side. So when you go into dynamic mode, there's some commands that are mutually exclusive with dynamic mode. One of them is the address command. So when we want to go into dynamic mode, we have to delete the address command because we're no longer calling out the peer's address. And instead, we use the dynamic command. But you can't hit enter. When you use the dynamic command, you must call out the remote IKE ID, which makes sense because the remote IKE ID, when it's not configured, is automatically inherited from the peer address. So if we don't configure a peer address because it's not a static peer, then of course we have to manually configure the IKE ID. So we're going to set it to a host name and we'll say SRX1. Now we need to do the same exercise on SRX2. So not only do we need to delete the address and set the dynamic mode with the IKE ID, we'll use SRX2 of course, but this command is also exclusive. This is how you set the remote identity when you're in static mode with the address command. When you're in dynamic mode, the remote identity comes right after the dynamic keyword. So if I were to commit this, I get an error. So I actually need to delete this remote identity command here since we're not doing a static peer. And now I'll be able to commit. So let's look and see how the situation has changed with IKE. So you can see here the peer that's 132, which is most likely SRX2, is up, and the 131 is still down. So the reason why SRX2 came up is because in the last lab, we already had the local IKE identity set to SRX2. So now that we set it on SRX0, things are looking good already. Let's take a look and see if that's the case. So yeah, SRX2, UDP 500 because NAT Traversal is still turned off. The two init and auth packets, and the remote identity is SRX2. So everything looks good here. Let's take a look at the IPSec. Yep, everything's looking good there. Let's take a look at the OSPF. Yep, OSPF is up. So all of my show commands should be happy. I have two bidirectional packets here for IPSec. So let's go ahead and ping the loopback and see how we look. So I'm going to ping 10.0.0.2 and I'm going to source it from 10.0.0.0. All right, there we have it. So let's do the same thing for SRX1. So let me jump over to SRX1 and we need to configure the IKE identity. So this local identity has to change. We're now doing host names. So we're going to say hostname SRX1. And that should do a replace. So you can't have both configured at once. So the inet's going to go away and the hostname is going to come into play. And that should bring us up here. All right, there it is. Up for 4 seconds. And I should be getting my routes. And I am. So I'm going to do the ping all the way to SRX2. So I'm going to ping SRX2 via SRX0. All right, and there you have it. So you can see here, using the dynamic IKE gateway, you can actually accept IKE peers without knowing their IP address. But you do have to know their IKE ID, and both sides have to agree what that IKE ID is. There's one more thing I want to say on using dynamic IKE peers before we move on. And that is, don't forget how the IKE exchange works. The proposals are exchanged in the init packets before the IKE ID is announced in the auth packets. This actually creates a got you for dynamic IKE gateway. If you're only using one dynamic IKE gateway, it's not a problem. You have one proposal, one policy, one gateway, and when the peer contacts the SRX, if the peer does not match a static IKE gateway, it automatically affiliates it with a dynamic gateway and offers the proposals of the dynamic gateway in the init packet. And because it's a dynamic gateway, it'll always be the responder, right? The dynamic side can never be the initiator because it never has the peer address to initiate the first init packet. Well, when you have two dynamic gateways, now you kind of have this issue where the SRX doesn't know which dynamic gateway the peer is coming from and belongs to. So it will always associate it with the first configured dynamic gateway. And because of that, if you have two or more dynamic gateways, they need to share the same proposals. So what's happening here is when SRX1 sends its init packet, SRX0 lands it on gateway SRX1, because at this point it doesn't really know who it is, so it just assumes it's SRX1. The proposals are exchanged in the init packets, everyone's happy, and then when SRX1 announces that it's SRX1 in the auth packet by saying its IKE ID, then SRX0 happily keeps it on gateway SRX1. But then when SRX2 sends its init packet, SRX0 again doesn't know which IKE gateway it belongs to, so it lands it on gateway SRX1 at first, and it offers the proposals offered by SRX1 gateway associated with the IKE policy. And once it makes it past the init stage and SRX2 announces itself in the auth packet, announces its IKE ID, then the SRX moves it over to the SRX2 gateway. And because of this behavior of where the IKE session is sliding around between the available dynamic gateways, they all need to share the same set of proposals. Now you can have separate policies, so you can have separate pre-shared keys, for instance, but they have to use the same proposals simply because those are what are exchanged in the init packet, and so those can't mismatch. Otherwise, it'll never make it to the auth packets, and it'll never figure out which dynamic gateway it actually belongs to. So again, this isn't a problem that affects when you only have one dynamic gateway, because it simply lands the peer there if it doesn't match any static gateway. But if you have two or more dynamic gateways, then essentially all your dynamic peers are just funneling into one gateway, so all your proposals have to match, and then once it gets to the auth phase or the auth packet, it determines through the IKE ID, oh, you're actually belong over here on this dynamic gateway, or oh, you belong over this way. So just keep that in mind. All right, so this brings us to problem 3, the final problem. And this problem is caused by NAT overload. So NAT overload has the same problem that static and dynamic have, where you have to set the IKE ID, but it has this additional problem here. And here you can see our NAT overload device. You can see the global IP that we're going to be NAT overloading everyone to, and you can see SRX1's local private IP. And look what the NAT device is saying. I can handle IKE, but ESP doesn't have ports, so I can't add it to my translation table. So this is referring to what we talked about earlier. IKE has UDP 500. It has no problem creating a translation on this shared IP address. But when ESP, the IPSec SA, travels through and traverses the NAT, it doesn't have a port number, so it can't make a translation table entry. So here it is restated, problem 3. NAT overload uses port numbers to translate, but ESP doesn't have a port. Solution is, if only one peer is behind the NAT overload, then IPSec pass-through should allow the translation. Otherwise, NAT-T and dynamic peer is needed. So I pointed this out. This is something we haven't even brought up yet. Some devices, modern devices by larger vendors, support IPSec pass-through. And what IPSec pass-through is it's kind of like an extension onto the normal NAT process, the NAT overload process, where it says, look, NAT overload, normally you need ports. But what if, instead of using ports, you just use the protocol number, right? So what if instead of using ports, you just use a protocol number, and that would at least allow one inside host, one local host, to use IPSec to the NAT. So for ESP, if you see IP protocol 50, make the translation based on the protocol 50 instead of by the port, because you won't find a port. And this actually works on most devices, most modern devices made by larger vendors. The problem is you can only rely on IPSec pass-through to work if you only have one host behind the NAT. if you have more than one host behind the NAT that's trying to send ESP traffic, immediately it gets confused because the binding is simply based on the IP protocol. So when the ESP traffic comes back, the NAT device will want to send it back to the only device that's sending ESP traffic. But if there's multiple devices sending ESP traffic, they're all using protocol 50. So now he's confused, back in the same boat. He doesn't know which inside host to return the ESP traffic to, and so it doesn't work. So you can't rely on IPsec pass-through all the time, but if you're in a pinch, it works. So let's take a look at this. Here's going to be our NAT overload topology. Again, just like with static NAT, just like with dynamic NAT, everything this NAT overload topology is going to be the same. We're going to have the same loopback IPs, the same interface numbers, the same tunnel IPs, and SRX0 is going to have the same global IP. SRX1 and 2 are going to have the same loopbacks and the same private local IPs and interface numbers. The only thing changing, and it's to bring attention to it, is the NAT global IP. So we're going to be using this IP ending in 20.254, and both SRX1 and 2 are going to be NATed to it. However, in this one, I'm going to have SRX2 with all of its security, including its IKE and IPSec, deactivated because I want this device to not say anything. I only want SRX1 to be saying stuff, and I want to show you what's going to happen. If SRX1 is the only device being NAT overloaded to this IP address, and it's the only device sending ESP traffic to this IP address, what will happen? Will IPsec pass-through kick in, and will it just work, or won't it? And don't forget, because we just finished the dynamic NAT lab, SRX0 is still set up in dynamic mode. So let's just take a look and see what we got. All right, so here we are back on SRX0, and nothing has changed since we completed the dynamic NAT lab, other than I disabled all security on SRX2, so no IKE, no IPsec. That way we only have one local host transmitting IKE and IPsec traffic through the NAT, and the NAT has changed from dynamic NAT and that IP range to NAT overload in the new IP. So let's take a look and see what that means for SRX0. What do we have here? So you can see we have IKE up. IKE is up to the new IP address. It's SRX1. The packet exchange looks normal. Still, NAT-T is disabled for right now. And I'm just demonstrating that IPsec pass-through can actually get IKE and IPsec up through a NAT overload. IPsec is looking good. OSPF is up. Oop. And let's do a ping test. So IKE is up, IPsec is up, we have end-to-end connectivity, OSPF is up. So this just kind of demonstrates that with IPsec pass-through, you could still get through a NAT overload without NAT traversal. Now this isn't me opining or encouraging you to not to use NAT traversal. I recommend you use NAT traversal. Take the 8-byte overhead on your IPsec because it's worth it. It makes the NAT device or the firewall that's doing NATing see your traffic as one stream. It's an industry standard. Other vendors play with it really well. So I recommend you using NAT traversal. I just wanted to show you this series of labs so that you could see the problems that NAT traversal doesn't solve, and how NAT traversal solves a very specific problem, and how IPsec pass-through can solve that problem if there's just one IPsec host behind the NAT. Now let's go back to our IKE configurations here because we're still in dynamic mode. So just for completeness, I'm going to take us out of dynamic mode and I'm going to put us into static mode. So I need to use the global address and I need to set the IKE identity. Now when I do this, this is going to clear IKE on SRX0, which is fine. But SRX1 IKE isn't going to clear. Now the reason why that's a problem is with the NAT overload, SRX0 can't be the initiator. He's going to try to be the initiator and is going to send a NIP packet now that we're back into static mode. But it'll never make it through the NAT overload because with NAT overload, only the inside hosts can initiate outward. So to fix this, I'm going to jump over to SRX1 really quick. And we're just going to clear IKE. And this will cause SRX1 to reinitiate as the initiator, and this should bring it up. So let's see. All right, so here we go. Let's see if that's SRX1. It is. Let's see if OSPF either came up or is still up. All right, OSPF came up. And let's make sure our pings are working between our loopbacks. And it is. So I just want to show that for completeness. You can use static peer or dynamic peer with NAT overload without NAT-T, so long as you have one and only one host behind NAT overload. So now, before we turn on SRX2, there's an interesting problem. We're about to have two gateways behind the same public IP, the same global IP. So right here, we already know before we even turn on NAT-T, we can't use static mode because the peer IP address is what the SRX uses to determine where to land the IKE session for exchanging proposals and etc. So if we have two gateways with the same IP address, then the operating system is just going to pick one, and that's not deterministic, and that's not going to ensure the right peer lands on the right gateway. When you're in static mode, your sessions aren't allowed to float around like in dynamic mode. So whichever one is picked, either the first or the second, that's what it's going to try to authenticate both SRXs against, and that's not going to work because the IKE identities aren't going to be the same. So we actually have to go back into dynamic mode. That's the thing you have to remember with NAT overload, is if you have multiple peers behind those types of NATs, you do need to be in dynamic mode. So I'm going to roll back one, and that's going to put SRX1 back into dynamic mode, which is what we want. Then let's turn on NAT Traversal. All right. All right, so we've removed the no NAT Traversal from both gateways. So now we're going to have dynamic mode for both SRX1 and 2, which we must have. And now we're going to enable NAT Traversal, which is going to allow two IKE and IPSec peers to be behind the NAT overload. So let's commit this. And let's jump over to SRX1 and clear the IKE, so it just reestablishes fresh. And oh, you know what? Let's turn on NAT Traversal, obviously, because it's disabled on this side too. There we go. And we'll just clear IKE again. And now let's jump over to SRX2, and we'll activate all the security, and we'll also turn on NAT Traversal. All right, so just because both tunnels are landing back on SRX0, let's look at it from SRX0's perspective. It might be a little easier. And now that SRX0 is in dynamic mode, it's going to be a responder always. So we show them as both up, where we can see where this responder. So now you see the NAT traversals in effect. So now we're on UDP 4500. Now you might be wondering, wait a minute, if SRX1 is using the global IP in port 4500, what is SRX2 going to use? It can't be the same, can it? And you're right, it can't be the same. So the NAT overload is going to translate to 1024, which is the first in the default range for Cisco iOS. So the destination port is going to remain 4500, but the source port is going to change when it gets natted in NAT overload. So everything looks good here. Let's take a look at our IPSec. Yep, everything looks good. Let's take a look at OSPF. Yep, everything looks good. So here you can see the what is actually being solved here, which is now NAT Traversal can come in and save the day and can allow us to do IPSec through a NAT device. You need it if the NAT device doesn't support IPSec pass-through. I recommend it through any NAT because it doesn't hurt. And you definitely need it if you're doing multiple devices behind a NAT overload, whether it supports IPSec pass-through or not. But now you can kind of clearly see with static NAT, you just have to mess with the IKE ID. With dynamic NAT, you need to set the IKE ID and you need to go into dynamic peer. And with NAT overload, depends on how many peers you have behind the NAT overload. If you have one peer, you can be in static mode, but it'll always be the responder because you can't initiate from the global side of a NAT overload. But I recommend being in dynamic mode because that's more realistic. And you can still keep NAT Traversal turned off because IPSec pass-through will help make the connection work. But if you're doing two peers, then you definitely need it. Let's go over to SRX2 and do our final test. So over here on SRX2, we'll do our final test, which is we'll ping SRX1 from SRX2. And this is via SRX0. And you can see it's working. All right. So there you have it, folks. Now you know all the different ways that you can do IPSec between two Juniper SRXs through a NAT, whether it's static NAT, whether it's dynamic NAT, whether it's NAT overload. The moral of the story is you always have to manually set the IKE ID of the NATed peer, and it's best to leave NAT Traversal turned on because it just makes things easy, but you only actually need it if you're going through a NAT overload and that NAT overload device doesn't support IPSec pass-through. You have more than one peer behind that NAT overload. And I almost forgot to show you guys the NAT Keepalive. It's really simple to configure. And just to review the labs we went through, you don't need NAT Keepalive with static NAT. Why? Because it's a static translation. It never expires. There's no timer. Then the question is, do you need it with dynamic NAT? Well, it depends, because remember, your IKE and IPSec are both being translated. Now there is a timer, but as long as you're using a protocol or something that's sending and receiving on IPSec, then you don't really need NAT Keepalive, because refreshing the entire IP to IP binding of dynamic NAT will keep your IKE and IPSec flowing in both directions, because they're both sharing the IP and the timer is against the IP, not against the port, right? So with dynamic NAT, you're only going to need NAT Keepalive if for some reason you're not running a routing protocol. Let's say you're not in route mode, or if you are in route mode, then you're doing static routes and you just don't send that much traffic across the tunnel. Then in that case, yeah, you're going to want a NAT Keepalive. Now, then when you come over to NAT overload, then it can get a little interesting. So if you're relying on IPSec pass-through, so your IKE is being translated on port UDP port 500, and your IPSec is getting translated based on IP protocol, then you're going to want NAT Keepalive, because now your IKE, which is very quiet, that eventually that timer is going to expire and you're going to lose that binding. And if you don't get the same binding back, which is very likely that you won't get it back, then that could actually clear out and reset your IPSec tunnel. So I would say if you're not doing NAT Traversal, and so you're going through NAT overload, and you're relying on IPSec pass-through, then you're going to want NAT Keepalive. However, if you're leaving NAT Traversal turned on, which I recommend for all NAT modes just to make it easy, well, now your IKE and IPSec are using the same UDP port. So now we're back to the same situation with dynamic mode, where as long as you're in route-based VPN and you have a protocol, there's going to be enough traffic to refresh the binding, the port binding, right? But if for some reason you don't have a protocol and you're doing static routing or you're doing policy-based VPN and it's just really quiet, then it might make sense to run NAT Keepalive. So let's see what it looks like. It's really easy to configure. It's going to be under the gateway. So we can turn it on right here for SRX1. And it's just NAT Keepalive. And it even says the interval at which to send NAT Keepalives. So, I mean, you can make this anything. You probably want to know a little bit more about the NAT you're going through, because some NATs will give you a binding for 24 hours. So like a lot of vendors with dynamic NAT or NAT overload for TCP, they'll give you a binding for 24 hours. Other NATs for UDP traffic, which is what IKE is, will only give you a binding for either 30 seconds or 5 minutes. It's kind of all over the place. I've seen 5 minutes a lot. For instance, Juniper is 5 minutes. I think Cisco is 5 minutes. So you're going to want to adjust this Keepalive accordingly. You don't need to send it out all the time. So we can set it for 30 seconds, for instance. And yeah, that's pretty much it. All right, folks, there you have it. Now you've seen 3 different labs showing 3 different types of NAT: static NAT, dynamic NAT, and NAT overload. And what we learned was NAT-T solves a specific problem with NAT overload, but it's on by default, and I recommend to just leave it on and just allow NAT discovery to cut you over to UDP 4500 to encapsulate ESP and UDP because it's an industry standard and a lot of vendors play well with that, including firewalls, and it makes your IPsec turn into a single flow, which is just easier all around for management and timers that you have to worry about. Additionally, you don't need NAT Keepalive if you're running a route-based VPN with something that's going to make sure traffic is being sent in at least one direction, for instance, a routing protocol like OSPF. So if you have NAT-T turned on and you're running OSPF, there's always going to be enough traffic on UDP 4500 that the binding's never going to expire. But there are some corner cases where you might have to turn NAT Keepalive on. For instance, you might need to turn it on if you're doing a dynamic NAT, but you're doing policy-based VPN or you're doing route-based and there's just no traffic going across. And so in that case, it might get quiet enough on the dynamic IP that it might surrender that IP. So no, I think normally the default though is 24 hours, so it would have to be a really quiet VPN. But nevertheless, administrators, they'll mess with those timers. So who knows, you might have to turn on NAT Keepalive. NAT Keepalive is normally one of those things that you leave off until you start having problems, then you turn it on to solve a problem that you've noticed with either a NAT device or a firewall you're going through. And then of course with NAT overload, I don't recommend relying on IPsec pass-through, because if some other device starts sending IKE and ESP traffic through the NAT device, it's going to mess up your VPN, it's going to cause problems. So definitely if you're going through NAT overload, use NAT Traversal, but I recommend using it at all times. But let me know what you guys think of this video. Thanks for watching. I know it was long, but I feel like we went over a lot of important things. So just leave some comments down below with some good feedback, and yeah, I hope that you stick around for my next video.